Hello everyone, welcome to Statistical Methods. In this video I will be discussing properties of statistical learning using Bayesian inference as exemplified on the beta binomial model. If you'd like to study this yourself, then check the lecture notes in chapter 9. So let's recapitulate the beta binomial model. So beta binomial model. So the beta binomial model is a standard model, standard Bayesian model for estimating a proportion. So if you recall, the standard likelihood model to estimate a proportion is of course the binomial distribution. So standard likelihood is the binomial. So whenever you see a name, model name in Bayesian statistics, if it has a composed name like beta binomial, then it's prior likelihood, so model. So this is how you write it. So beta binomial means beta prior and binomial likelihood. Okay, so what are the results that we got from this model? So essentially we start with a beta prior. And this beta prior, beta alpha beta, has two parameters, and these are called also hyperparameters because they are parameters of the prior and not of the likelihood itself. So we start off with a beta prior, and then we define m as alpha plus beta, and then we get a beta posterior. Because we use the binomial likelihood, we get a beta posterior with beta alpha plus x and beta plus n minus x. So if you recall, let's say alpha is the parameter for heads, then x is counts of heads, then n minus x would be the counts of tails. So basically what we have here, x and n minus x, is the influence of the data. So, and that's exactly what we're doing in Bayesian statistics. We go from a prior that describes our uncertainty of a parameter, in this case p, with data, to the posterior, and so there is no wonder that the posterior actually includes the data, and it also includes the prior, and the prior is characterized by these two parameters. And it turns out, so that's the first property, so prior acts as pseudo data. So it really acts like data, and what you see here is this alpha and the beta, they are actually pseudo counts. So these pseudo counts, they are exactly, so alpha is the pseudo count for the heads and beta is the pseudocode for the tails. So they really are acting as data, and the m equaling alpha plus beta, m is basically the pseudo sample size. So n is the actual sample size and m is the pseudo sample size implied by the prior, by the beta prior. So what does this mean? So normally the more sample size we have, the more sure we are about something, so the lower the variance, and that's actually exactly the same with the prior. So we can see that, let's say we know that the beta 1, 1 would be the uniform, so it's uniform between 0 and 1. But if we increase the sample size, so let's say we have beta 10, 10, then this would actually look more like this. So it's still symmetric because alpha and beta is the same, but it's concentrated around the mean. The mean is of course 1/2 for beta 10, 10, and so we are far more sure about this, and this also influences, of course, our posterior, because if we have a strong prior, then we have a strong impact in the posterior as well. And this is also seen that alpha and x and beta and n minus x are treated exactly on the same footing. So that's one thing. So basically, and that's also what you have to keep in mind. And if you have a prior in the model, you're actually inventing data. And that's a good thing, mostly, because we would like to find a method that works well if we don't have enough data, enough actual data. So the solution is actually using priors that basically fill in data. So this is useful if sample size is small to avoid overfitting. So we've seen, or I've told you before, that likelihood methods are prone to overfitting, and also we know that they're not optimal. If there's small sample size, they're only optimal for large sample size, and so for small sample size, it's the mechanism to bring in the extra information is the prior. So prior is a mechanism to bring in extra information. So that's the first point. So prior is actually acting like data. So the second interesting thing is the following. So if we look at the mean, so we have posterior mean and prior mean. So the prior mean in the beta so the expectation of P is alpha over m, and the posterior mean E of P given x is x plus alpha divided by n plus m. So for comparison, the maximum likelihood estimate is x over n. So we have here on top the pseudo count for the heads, and then here we have the total sample size. So it's really like we have extra information again. But the key thing is now to note something else, namely that we can rewrite this as follows. So we can write, so this is our mu prior, and this is our mu posterior. So we can write this as follows: mu post equals a factor lambda that I will explain in a second times mu prior plus 1 minus lambda mu head maximum likelihood. So this would be mu ml. So we have three things here: this one, and this one, and this shows up here, here, and here, with lambda in this case equaling the n over m plus n. So lambda is the proportion of the information, the sample size available in the prior compared to the total sample size. So proportion of implied sample size versus total sample size. So, and this is called the shrinkage intensity, and this number is, so because m can be 0, but it can also go to infinity. In this case, the lambda is in the interval 0 and 1. And this thing here, what you see here, basically you can see that the prior mean is an update of the maximum likelihood. So if lambda is 0, so lambda 0, then we get the mu post equals mu hat ml, and if lambda equals 1, then mu post equals mu prior. So basically what we have is that the posterior mean is a convex function, or not convex function, convex combination of the likelihood, or not the likelihood based estimate, so the MLE, and prior. So we can really see that in this case, and also for other cases, so that's actually quite a general effect, that by a linear update of the maximum likelihood estimator, we get the Bayesian estimate. So in short, the base posterior mean is an updated or adjusted maximum likelihood estimator. So we're basically improving the maximum likelihood estimator by adding the prior. And the interesting thing is also, if n is large, so if n is large, so n large, then we basically get lambda equals 0. because then m can be whatever it will be. If it's constant and n goes to infinity, then lambda will be large. So if it's large, we will actually recover the maximum likelihood estimator. So large n, we get the MLE. So that's fantastic, because it means that the ML is really an integral part of Bayesian learning. And if the sample size is large, then we get the MLE, which is no surprise, because for large n, ML is optimal. So we want the best. And that means, because we want the best for large n, we get the best in this approach. We get maximum likelihood for large n. But for small n, we get something else. And we'll see that for small n, it's actually, this is the best. Okay. So that's the second property. Second property, so second property was linear shrinkage, and this linear shrinkage, that's the case for this example, but it's also case for many other models. And these many other models are particularly in the so-called exponential family. So exponential family is simply normal distribution, binomial distribution, and many other distributions, and exponential distribution, etc., etc. So it's a large family, and in all of these you can show that there is linear shrinkage. Okay, so let's continue with the investigation of the properties. So the next property is something that we've observed, namely we had beta prior and a beta posterior. So if you have, so if prior and posterior are from same family, then this has a name, and this means we have a conjugate model. So conjugate prior or conjugate prior so there are nice models to work with. So you need a certain, so it requires a certain combination of prior and likelihood. So you can, that's why you also say beta prior is conjugate with binomial likelihood. So the conjugate has a several, you can say either the prior is conjugate, but then you also need to specify the likelihood. Or you say the prior and the posterior are conjugate. In any case, this is a very special case. So posterior and prior are from the same family. That's special and not necessarily always realistic to have, but it's very useful for calculations, especially if you want to do it analytically. So In the exponential family, these models, they have the advantage that you can always find conjugate priors and conjugate likelihoods, so they are simple to use. So the next thing is, let's look at the asymptotics. So we've already looked a little bit in the asymptotics. So we know that if n is going to infinity, we know that we've seen that mu post, now I write ahead because it's an estimator, becomes asymptotically the mu maximum likelihood. And the key thing is also, so if you look at the posterior variance, so for the beta binomial, it also becomes asymptotically the maximum likelihood variance. So, which means for large n, the Bayes estimator turns into the ML estimator, and the interesting thing is actually something that's kind of a little bit subtle, because this here is the posterior variance, or let's put it this way, the variance of posterior distribution, and this is actually the variance of the sample distribution. So the intriguing thing is that for large n, they converge. So the variance of not just the variance, the posterior distribution becomes this same form as the sampling distribution in the limit. So that's interesting, and this also leads directly to so we know that, so asymptotically, so in regular models, we know that this is normal, asymptotically normal. And this is actually the same here as well. So this is called the Bayesian central limit theorem. So the Bayesian central limit theorem states that for large n, the posterior distribution converges to a normal. So for large n, converges to a normal distribution. Centered around the MLE. So this is exactly the same thing. So it's not just the mean that converges, it's not just the variance that converges, it's also the distribution that converges. So distribution, the posterior distribution converges to normal or multivariate normal, just like ML. So that's nice. So the asymptotics are very good. And then finally, of course, we're interested also in the finite setting, so finite n. So that's where things become interesting. So let's recall. So for beta binomial, we had the mean, so was the posterior mean x plus alpha divided n plus m, so that's cost mean, and the posterior variance was p base times, so let's call this p base, times 1 minus p base divided by n plus m minus 1. So the interesting thing is, so finite sample size, for finite n, posterior variance is typically smaller than the corresponding variance of the MLE. And the reason is simple. Reason is the pseudo data. We have more data, even if it's pseudo data. So, and because we have more data, the variance is, even if slightly, is small. So this hints again that for small samples it's beneficial to actually add prior information using extra information using a prior. That's it for today. So you can, even from this simple beta binomial model, you can learn a lot about Bayesian statistics. And in the next video we'll talk about two further basic models that are always appearing in Bayesian statistics. So see you in the next video, and bye bye.